This particular review session will be over acceleration. And the first thing we learned when we talked about acceleration was that acceleration was the change in velocity over a period of time. Its unit is m divided by s squared, or meter per second squared. And it can also be written as meter per second per second. All right, so meaning that there is a velocity change over a time. All right, so that's what acceleration was. Now, acceleration, one thing that you need to know about it is how the graph looks, how a graph looks for acceleration. Okay, so there are three graphs associated with acceleration, and those are these: velocity versus time, acceleration versus time, and distance versus time. Okay, in a graph that is acceleration versus time, if it is going at constant acceleration, the acceleration graph will just be a straight line across. All right? If you're looking at a velocity versus time graph, the velocity versus time graph should be a straight line up, a linear graph. All right? Just a straight linear line. And then the distance versus time graph will be curved. Okay? Now, let's look at the formulas associated with acceleration. Okay? The first formula that we dealt with in association with acceleration was this: A is equal to VF minus VI divided by T. Okay? If we take a second to rearrange that, just real quick, multiply the T up, acceleration times time, equals VF minus VI. And then if I put AT plus VI equals VF, we can see that we can use this to either solve for acceleration or final velocity. You should also be able to see that you could solve for time fairly easily by doing this formula, and you could do VF minus VI over A equals T. So you can use this formula to solve for a lot of different things. The important thing here is that if you're looking for final velocity and you're dealing with acceleration, this is the formula you should probably start looking at. I would also say this real quick: if we look at this formula and we do a graph of velocity over time, you should very easily see that the reason a velocity versus time graph looks the way it does is if we replace the t with an x, we would get ax, and if we place the v's with a y, then what we would get would be plus the y-intercept equals y. And so you should see this is a linear formula, which explains why the v versus t is a linear graph. All right. An example of this problem would just be you have an acceleration of 5 meters per second and initial velocity of 2 meters per second. How long would it take to get to a speed of 10 meters per second? And the way you would do this would be you would start off A is equal to VF minus VI divided by T, and plug in your numbers. 5, that should be squared, 5 meters per second squared equals 10 minus 2 divided by T, and then solve for T. We have to get T out of the bottom, so we multiply T to both sides, and we would get 8 equals 5T, or T is equal to 8/5 of a second. Now, it is important to note that if you're solving for acceleration, the acceleration can be negative. All that means is that it's slowing down. All right, so the acceleration can be negative. It's just slowing down. The other formula that we talked about, the other major formula that we talked about was this: D is equal to 1/2 AT squared plus VIT. Now, again, if we do the little graph real quick, just let me show you. D over T, or D versus T. If you replace the D with the Y and the T with the X, you should see that it's Y is equal to 1/2 AX squared plus some number X. And so, if we look at this, this is a good little parabola. So that's what it should look like. So if something's accelerating, It is a parabola. Now, this formula is terrific for figuring out acceleration, or sorry, for figuring out the distance, but keep in mind you can also use it to figure out the time, especially if the initial velocity goes to 0. It's very easy to figure out the time by rearranging this and doing d divided by 1/2 a square rooted equals t. So like you can rearrange the formula very easily to find time. All right, so don't forget to do that. I'm not going to work out a problem with this one just because, hopefully you've seen this enough by now. I'm just trying to remind you what formulas we have here. The last thing to remember is that the V average formula still works, okay? This is the distance over time formula. It still works. So like if something's accelerating and has an initial velocity of 5 and a final velocity of 15, that's okay. You can still find the average velocity because if it's constantly accelerating, it should be an even number. But in addition to it being equal to the distance divided by time, the average velocity for our stuff here can also, if it's constantly accelerating, VF plus VI over 2 is also equal to the average velocity. Now I want you to keep in mind, this is only good if it's constantly accelerating. If it's not constantly accelerating, that is not good. So for instance, if it was like the problem we had before where it was 5 meters per second for 2 meters and then 10 meters per second for 40 meters, what's the average speed? That won't work for that. It'll only work if you have a situation like this where it's 5 meters per second, 15 meters per second, and then you have an acceleration of constant acceleration of 2 meters per second. You could use this formula. Also, this formula is good because if you have it, you know d over t is equal to vf plus vi divided by 2. And so it can allow you to solve for the distance or the time if you don't know the acceleration of the thing particularly. You can use this to find the distance without having to solve for the acceleration. Or you can use it to find the time if you don't have the acceleration. Okay, so that's the third formula. The last formula is not really used all that much, but we did use it, or we did see it, and it is on the formula chart. So I'll go ahead and show it to you. A is equal to VF plus VI, VF squared plus VI squared. I apologize, that's not plus, it's supposed to be minus. Minus VI squared over 2D. Alright, now, this formula is useful if you do not have the time and you need to solve for the acceleration, the final velocity, the initial velocity, or the distance. Normally, you can just use, these formulas here, either this one or this one, and just solve for them, and then solve for time in one and plug it into the other one. But if there is an initial velocity, that means you would have to do a quadratic formula, and this formula allows you to avoid needing the time if you have an initial velocity, because it throws off that distance formula. If you want to know what I mean, just try to solve the time. If I said the distance was equal to 15 meters, you had an initial velocity of 30 meters per second, an acceleration of 4 meters per second squared, and a final velocity of 50 meters per second. All right, try to solve for the time. Well, you know everything, right? So it should be easy. 1/2 at squared plus vit. But if you plug it all in, you would get 15 equals 1/2 times 4 times t squared plus 30 times t, and then you have to do the quadratic formula. And nobody likes doing the quadratic formula. So instead of doing the quadratic formula, if you have a situation where this data is available, go with this formula. It will greatly, make your day much, much easier. It's certainly easier than negative b plus or minus the square root of, I don't even know, blah, 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 divided by blah, blah, blah. All right? So that's what that formula is for. All right? That ends our little lesson over acceleration.